If you're watching this video, there's a 99% chance you have searched for something on Google, Amazon, YouTube, Wikipedia, you name it. Whenever you enter a bunch of characters into a search bar, a sorting algorithm uses your search to generate, for example, most popular or relevant results, least expensive products, items in alphabetical order. A sorting algorithm is, well, a computer algorithm that sorts items in a dataset, like an array, list, or string, into a particular order. There are several different types of these algorithms, each with their own efficiency levels and ease of programming. Insertion sort is one of these algorithms. Although it is quite slow compared to other algorithms, as will be explained later, it is one of the easiest to code. Insertion sort works using two iterative loops. The first loop is a for loop which goes through every piece of data in the dataset once. The second loop, nested within the for loop, is a while loop which continuously moves the datum left or right as long as it is larger or smaller than another datum adjacent to it. The code shown here sorts integers in an array from least to greatest. Speaking of which, let's see how insertion sort exactly does this amazing function. Here, we are presented with an integer array consisting of 5 unsorted elements: 18, 6, 15, 9, and 3. They will need to be sorted from least to greatest, and insertion sort thus will check the datum preceding the selected datum during each iteration. When iteration begins, the algorithm looks at the first element in the array, 18. Since there is no element before it that needs comparison with 18, it stays in that position. The algorithm then selects the next element, 6, and compares it to a previous element. Since 6 is less than 18, the elements swap the indexes. 6 has hit the beginning of the array, so it needs not move left anymore. Next, the algorithm selects 15 and compares it with 18. 15 is less than 18, so we swap. 15 is then compared with 6. Since 15 is greater than 6, it has found the correct index, and the elements will be placed there. Then, 9 is compared to 18, less than, then 15, less than, and then 6, greater than, and it is placed accordingly between 6 and 15. We have now come to the final unsorted element in the array, 3. It will have to be compared with 18, 15, 9, and 6, all of which it is less than. Since 3 will arrive at the beginning of the array, it will cease its movement and establish its position as the first element in this now sorted array. Now that we've gone over the workings of insertion sort once, let's go over them again. This time though, I'll be demonstrating a larger array using real-life cups, and will definitely not be promoting this channel in the process. As I said, in insertion sorts, the algorithm goes through the dataset once and moves every piece of data down into its proper ordinal position. The S and T in this array have no need to be moved down, but the A has to go at the beginning of the array. The N needs to be before the S and T as well. Next, the algorithm inserts the M into its correct position between A and N, and then looks for the correct place to put the E, which happens to be between A and M, and drops it there, and so on and so forth. Next in the array is L, then I, then X, which is already farther than everything before it, then G, then the second A, then the second M, then the second E, and finally the second S. And we're all done. In computer science, the big O notation is the number that conveys how an algorithm's runtime and space complexity increases the more inputs there are into the algorithm. There are several time complexities, as shown in this graph where the x-axis is the amount of inputs, and the y-axis is the average runtime. They range from big O of n exclamation mark, factorial time, which is the very worst out of all of them, to big O of 1, constant time, which means that the algorithm will run almost instantly. If you don't know what a factorial is, look below. In the case of insertion sort, its big O notation ranges from big O of n, linear of time, to big O of n to the power of 2, quadratic time. The best case scenario for the insertion sort algorithm to run smoothly is when every datum in the set to be sorted is already sorted in the first place. Because of the fact that insertion sort goes through the dataset only once, the absence of swaps means that the algorithm has to make only as much comparisons as the number of data in the set, causing it to run in linear time. The average and worst case scenario for insertion sort is when every datum in the set needs to be sorted. For example, if you have a size 20 array sorted from greatest to least, you would need to make 190 swaps in order to make it least to greatest. In this case, the algorithm runs slightly faster than quadratic time, which means that the amount of needed comparisons totals to the number of data to the power of 2.